Okay, so thank you for coming to the next CDY talk. And our speaker for today is going to be Ellen Zweibel, who's going to talk about cosmic rays and galaxy formation. And I'm one of the instigators of the talk. I thought it was important because if you go to other astronomy talks out there, you will hear all about cosmic rays revolutionizing the world of galaxy formation, basically cosmological simulations where galaxies like the Milky Way come from. But on this side of the universe, we never talk about that kind of stuff. So and observations from TV instruments in principle can help put constraints on cosmic ray propagation and the cosmic ray spectrum and things like that. So I think it'd be useful to confront sort of observations and different uses of cosmic rays all in one place. And Ellen Zweibel, I think, is uniquely placed kind of in the middle of it. She understands the plasma physics, but she also talks to the cosmology simulators. So I hope she can tell us a bit today about what's going on. And as far as Ellen herself, she did her undergraduate work, I guess, in mathematics at the University of Chicago. And then she went to Princeton for graduate work in astrophysical sciences. And then she went to the University of Colorado, where I think I first met her. And then she moved to Wisconsin, where she is now. And she's a W.L. Kroshar Professor of Astronomy and Physics and the director, I think it's still an NSF-funded center for magnetic self-organization and laboratory and astrophysical settings. Is that right, Ellen?
Well, no, actually,
Nope.
I can't get that off the webpage, but we're doing other things.
Okay, that's important. But Ellen has had a lot of students and perhaps postdocs working hard on this problem, so I hope she can tell us about this today. And if you have, I guess we were talking beforehand, if you have questions for Ellen, feel free to interrupt her or raise your hand and we'll do that. Otherwise, let's wait till after roughly 50 minutes and then we can ask all sorts of questions at that point. So if Ellen's ready, we'll get started then.
Okay, thank you, Paolo. Can everybody hear me? So I really do encourage questions. I made this fairly short talk in terms of number of slides because I would really love to have some dialogue with all of you. So I'll tell you in a minute why I call this a provisional summary of cosmic rays and galaxy formation. I want to name my collaborators. So on the top line are various students and postdocs, either now or formerly at University of Wisconsin that I've worked with: Chad Bustard, Rourke Habiger, Evan Heinz, Josh Wiener, and Sherry Wong. And then I'll also highlight work by some of my collaborators who are not at UW: Ryan Farber, Peng O, Mateusz Roskowski, and Karen Yang. And I've been generally supported by the three entities with logos on the bottom. So why is this interesting, and why is it only provisional? It's interesting because cosmic rays form a significant part of the interstellar energy budget. There's good theoretical and observational evidence that they're implicated in feedback, both star formation feedback and black hole feedback. They must have an impact on the circumgalactic and intergalactic medium, and they could even play a role in the galactic dynamo. Why is this provisional? Well, the picture of galaxy formation is evolving rapidly thanks to JWST and other observations. So I'm not going to try to evaluate the observations in this talk. I don't know how to do that, but I am going to go into a fair amount of detail on how the interactions of cosmic rays with their host medium and their effects really depend on how cosmic rays are transported, which is characterized by interactions with microscale fluctuations. And I just want to underline, so transport theory depends on the physics of waves and turbulence. And remarkably, this is really one of those cases where the effects of kinetic scale plasma waves, by kinetic scale, I mean something less than the size of our solar system, these waves and instabilities have effects which print through at the largest scales. even going up to megaparsec scales. So I think we really, what I'm hoping mainly to convince you of is that we cannot avoid going into this plasma physics. Okay, so the plan of this talk is cosmic rays at a glance, and I really do mean a glance. It's a luxury to be able to talk to an audience that knows a lot about cosmic rays. Doesn't often happen. Then I'm going to give a brief review of transport theory, and I'm not going to show a lot of detail. The 2017 paper that I put on the reading list does go into that detail, but it's necessary, I think, to say something about this because the two main goals of transport theory in this context are to characterize how cosmic rays exchange momentum and energy with a thermal gas, and how we can derive a fluid theory that describes cosmic ray interactions at large scales. So we're seeking, despite all the detailed information about the cosmic ray spectrum, we're seeking a model for the bulk effects that we can put into global simulations of galaxy formation and evolution. So I'll talk briefly about those things, and then I'll spend most of the talk actually talking about some results we've had and how they depend on our models of cosmic ray propagation. And the examples that I've selected are restructuring the interstellar medium. That sounds ambitious, so I'll explain what I mean. Galactic winds and star formation feedback, and the concept of an Eddington limit for cosmic rays. Then I'll just summarize and talk about what I think are some important future directions. Okay, so these are the salient properties of cosmic rays for the purposes of this talk. So, of course, we have beautiful cosmic ray spectra showing the effects of the contributions of many different missions and observing techniques. But this is sort of a theorist spectrum because it shows that cosmic rays are, to a good approximation, a power law or a broken power law over many, many orders of magnitude. So the important thing for this talk is that the spectrum is a declining power law in energy. What you can't see from this spectrum is that most of the energy density and pressure come from the proton cosmic rays, the most abundant form, at a few GeV. So this is the part of the spectrum that carries most of the pressure and the energy density. This shows that cosmic rays are highly isotropic in arrival direction. So although they probably come from discrete sources like young supernova remnants, their arrival directions are scrambled by the interstellar magnetic field on all levels, and they arrive at the Earth more or less isotropically to well under 1% anisotropy. And we know from spallation data and to some extent from nuclear cosmochronology that cosmic rays are confined in the Milky Way for about 10 million years at GeV energies. And then the confinement time goes down for more energetic cosmic rays. Okay, so these are the main observational properties of cosmic rays that we're going to use. So what are the challenges? So here's a beautiful magnetized spiral galaxy. It's magnetized, the sort of palsied curve here is my attempt to draw what the magnetic field sort of looks like. So in spiral galaxies, magnetic fields tend to be azimuthal, sheared out by galactic rotation. There's mostly in the plane of the disk, although there are some exceptions. And although there's long range order, there's also small scale fluctuations. If we zoom in, maybe on a little piece here, so here in black is a field line reflecting a prevailing orientation, but also some scrambling of direction. And what cosmic rays seem to do is scatter up and down the field lines. So they mostly follow the field lines, but in fits and starts. They go forward and backward. And these two effects together, the sort of wandering, somewhat stochastic nature of the galactic magnetic field and the presence of small-scale scattering determine how cosmic rays propagate within a galaxy. And the actual scattering mechanism is something called gyroresonance scattering, and I've kind of depicted the main effects at play over here. So this red curve is a magnetic field line, and it displays both large-scale curvature and small scale, tiny scale fluctuation. And this helix here is the orbit of a cosmic ray. And it pretty much follows the large scale curvature of the field lines. And it pretty much averages out the tiny scale fluctuations. But there is a scale, which is actually kind of hard to draw, where the cosmic rays do interact strongly, and that is right at the gyro scale. And when I'm talking to an audience that's localized in a particular place, I like to make a sports analogy. So, you know, sometimes it's surfing, your surfboard is exactly the length of the crest between the waves, or if it's bicycling, your wheelbase is just the size of the mogul and so on. But for this international audience, I won't attempt to do that. I'll just say that gyroresonance scattering is the strong interaction of cosmic rays or any particle with fluctuations on a scale of their own wavelength. Okay. So how do we put this into a transport theory? So the fact that cosmic rays are so isotropic is really, and confined to the Milky Way for a long time, is really what gives us hope that we can develop a fluid theory for cosmic rays. So in an ordinary gas, you know, just particle collisions guarantee a short mean free path, and the gas comes to some kind of equilibrium. We know that the cosmic rays don't come to anything like a Maxwellian. They have a power law distribution in energy, but they do seem to be very well scattered with a short mean free path, which we can infer to be about a parsec at GeV scales. That comes from comparing the size of the galaxy to the confinement time and assuming some kind of random walk. And this is what allows us to develop a fluid treatment. So there are basically two classes of propagation model. So here on the left is what we call streaming or self-confinement. And in this case, we assume that the gyroscale waves that the cosmic rays scatter from are generated by the cosmic rays themselves as they stream down their pressure gradient. The theory for this goes all the way back to the late 1960s to Russell Kulsrud, Don Wenzel, and their students and collaborators. What this results in is a streaming relative to the gas at the Alfvén speed determined by the density of the plasma. So not the whole gas component. If you have a weakly ionized medium, what counts is the density of the plasma. So the Alfvén speed in the interstellar medium with respect to the plasma is usually typically a few tens of kilometers a second. Because the cosmic rays are passing energy and momentum to the waves as they excite them, and in a steady state, the waves must be transferring energy to the thermal gas, there's a heating mechanism, which it turns out you can write in this kind of simple, intuitive way as a sort of frictional heating. It's the scalar product of the Alfvén speed dotted with the cosmic ray pressure gradient. So it's kind of V dot F. We can think of it that way. We can show that when cosmic rays are streaming at the Alfvén speed along the magnetic flux tube, their pressure follows this, what looks sort of like an adiabatic law. Their pressure is proportional to the 2/3 power of the density. And we can interpret this, even though it looks like an adiabatic law or a polytropic relation, it's really more a consequence of the equation of continuity, because if the density goes up, the alphane speed goes down, and the cosmic rays tend to kind of pile up, and they pile up in this manner. It's not a standard adiabatic relation in the sense that if the density is changing slowly with time, the cosmic ray pressure does not necessarily follow this law the way it would in thermodynamics. Okay, we'll say more about this. This leads to some kind of interesting mesoscale or large scale effects, which I'll get into later when I tell you about bottlenecks. Okay, so the alternative is that the waves that the cosmic rays scatter from are not produced by the cosmic rays themselves. They're produced by an interstellar cascade or something like that. I'm going to call this the extrinsic turbulence model. And in the extrinsic turbulence model, the cosmic rays just have some diffusivity, kappa, which is determined by the properties of the cascade. In the limit that the diffusivity is very small, the cosmic rays are just advected with the gas. They're essentially kind of frozen into it. And then they just behave like any other relativistic gas. Their pressure is proportional to the density to the 4/3. Now, in all these models, the cosmic rays exert a force through the gas, on the gas through their pressure gradient. What the pressure gradient is determined by the confinement physics. But whatever that pressure gradient turns out to be, the cosmic rays exert a force that's proportional to it. In the self-confinement case, there is this heating that originates from the fact that cosmic rays are passing energy to the waves. But in the diffusion and advection models, there is no transfer of heat, assuming that is that the turbulence is balanced, has equal intensities in both directions. So, these models have a lot in common. In both of them, the cosmic rays interact with the gas mediated through gyroscale waves. The only difference really is the origin of the waves. But what I'm going to show you is that the outcomes are really very different. So again, I want to make the case we have to get this right. Okay, a little bit more about the waves. So I've talked about how they're excited or how they originate. How about how they're damped? So if you have a weakly ionized medium, since the waves are just propagating in the plasma component, ion-neutral collisions will damp them. And this turns out actually to be quite a strong damping mechanism. In a fully ionized plasma, the waves are also damped by processes which we don't understand as well, I think, as we understand ion-neutral collisions. So there's a process called turbulent damping, which was discovered about 20 years ago. And the idea of turbulent damping is that as the waves propagate down a background magnetic field, which is structured, particularly on small perpendicular scales, those waves kind of get sheared apart. And eventually, they probably damp viscously, but for the purposes of cosmic ray scattering, they become useless once they're sheared because they're no longer resonant. So we can consider that a damping mechanism. There's also a nonlinear damping mechanism where if we think of the waves as kind of forming packets of varying strength, thermal ions can absorb energy, not from the fluctuation itself, but from the envelope created by the overall shape of the wave pulse. The damping is important because in self-confinement theory, the cosmic rays stream at a rate which is large enough to offset any effect of damping. So if the damping is very weak, they stream essentially at the alphane speed. But if the damping is strong, they've got to push on the waves harder to overcome that damping, and that leads to a greater anisotropy and a faster streaming. And in the extrinsic turbulence theory, the damping affects the properties of the cascade. So for example, if ion-neutral damping is very strong, that really takes a bite out of the cascade at scales that are much larger than the cosmic ray scales. And of course, a pervasive question that I'll come back to is, have we identified all the relevant damping mechanisms? Okay, so now I want to show you some ways in which our choice of propagation model affects the results at large scales. So let's start with structuring galactic discs. So this is a cartoon from the original paper by Gene Parker. Is there a question? Okay, I guess not. This is from Gene Parker's original paper in 1966, where he described what's come to be known as the Parker instability. And the way that works is if we start with a medium that's just vertically stratified with straight magnetic field lines and cosmic ray pressure, there's a source of free energy in that magnetic pressure and cosmic ray pressure kind of suspend the thermal gas above its natural scale height. So if that energy could be extracted, the system would find a lower energy state and the state of the system would be different. And Parker realized that a way to do that would be to bend the field lines. And if you bend the field lines into this somewhat exaggerated shape, thermal gas will slide down into the pockets. It'll slide down under the force of gravity and reduce its gravitational potential energy. But the energy that's gained by lowering the gas is offset by the energy cost, which is the work that's needed to compress the gas and to bend the field lines. And so whether medium is Parker unstable or not depends on how compressible, what the equation of state is for the medium that you're trying to lower the energy of, and what modes are allowed, or what wavelengths are allowed. So Parker argued that this would restructure the interstellar medium. The connection to the galactic dynamo was posited somewhat later, and this instability has also been invoked in accretion disks. So it's really kind of worked its way into the canon of important astrophysical instabilities. Now, I put an asterisk here to highlight the fact that Parker's paper was published in 1966, and the theory of the streaming instability and its consequences was not introduced until 1969. So Parker assumed in working out the growth rate of his instability that the cosmic rays essentially act like a gamma equals zero fluid, that they just zip up and down the field lines and there's no energy cost in compressing them. Okay, in other words, that they would contribute to their pressure gradient would contribute to the equilibrium, but they would just kind of get out of the way when it came to the instability. So we went back several years ago and looked at the consequences of a more modern treatment of cosmic ray propagation in the Parker instability. And what we found is that if you assume the cosmic rays are frozen into the gas, so this is the advective transport model, they have this fairly stiff equation of state with gamma equals 4/3. To the extent that they're not relativistic, it's even larger than 4/3. And so it takes work to push them down there into the pockets. And this is dramatically reflected in the growth rate of the instability and which modes are unstable at all. So here on the left is what we call classic Parker. So it's Parker with zero adiabatic index for the cosmic rays. And here is Parker with gamma equals 4/3. And I don't know if you can read these scales very well, but the scales are different. Here, the fastest growth rate is about 0.6 in units of the sort of canonical gravitational buoyancy frequency. And here it's only 0.01. And here, the wave number scale goes up to 1.4 in units of an inverse scale height. And here it only goes up to 0.3. So there's really only a tiny domain of instability, and it's very small. If you redo the problem with either streaming transport or diffusive transport, you find that these effects are destabilizing. And streaming in particular will take the growth rates not only back to classic Parker, but even beyond. And there seems to be a coupling to a thermal instability that I worked on many years ago with Mitch Biegelman. Okay, so that's kind of the state of linear theory. And then we did some nonlinear simulations, and we found that the Parker instability, if you give it enough time, the Parker instability works as advertised. So what you see here, so there's an initial state of magnetic pressure, gas pressure, cosmic ray pressure. This is unstable according to sort of any Parker instability criterion. And then we ran the Parker instability with two different models of cosmic ray transport. One being diffusive transport, that's the dashed line, and then streaming transport, that's this type of line. And we found that in half a gigayear, the interstellar medium has been substantially restructured. The cosmic rays and magnetic field form kind of a thick disk, as they're observed to do in our galaxy, and the effective scale height of the gas is lower. And there's a significant difference between the predictions of the diffusion and streaming model as far as the gas is concerned. The cosmic ray and magnetic field evolution is pretty similar, but if you include heating, which is a natural consequence of the streaming model, the gas layer is puffier than if you don't heat by streaming. Okay, so the Parker instability does what it should do, but this is a very slow process. A lot of things happen in the interstellar medium in half a gigayear. There's also this what seemed to me kind of paradoxical, really never stopped nagging at me. And that's this result that if you assume the cosmic rays are advected with the gas, so very small diffusion coefficient, that they're actually stabilizing, not destabilizing. And this kind of flies in the face of our expectation that cosmic rays should be buoyant. They have pressure, but no mass. So how is it that in the end, in this treatment of their propagation, they show up as a stabilizing effect? Okay, so to kind of get at these questions, to understand a little better cosmic ray buoyancy, and see if we could bring the timescales down in any way, Werk Habiger, who's a grad student currently in my research group, and Sherry Wong, an undergraduate who will be applying to grad school in a year or two, undertook a kind of localized injection study. And the idea here is, let's just look at this bundle of field lines. So we inject cosmic rays impulsively, about 10 supernovae worth of cosmic rays, onto a magnetic flux tube in a stratified galactic disk. And we have a series of actually 10 simulations with different background properties and different cosmic ray transport properties. And these three columns each represent a different propagation model. This one is advection, this one is streaming, and this one is diffusion. And so in 3 mega years, not very much has happened. You can kind of see the injection. This is cosmic ray pressure that's shown over the base pressure. And then you start getting a largish perturbation. So the scale here is 1 kiloparsec in either direction, and it's a box that's 2 kiloparsecs high. And very importantly, there's a dimension out of the page as well, which I think in this case is only about 100 parsecs, but it turns out to be enough. And then as we follow things along, in 120 mega years, the advection and diffusion models have made nice big perturbations. These field lines have risen a lot. They've created a cavity which is much bigger than the initial cavity that started where the cosmic ray injection was. That was only 40 parsecs in size, but under the influence of buoyancy. So it's, as Parker realized, it's a kind of self-perpetuating process. As the field lines arch, gas flows down them, and you get these big arches, except in the streaming model. So in the streaming model is sort of going in the right direction, but it has had much less of an effect after 120 mega years. And to the extent that I've spent a lot of time working on the plasma physics of the streaming model, this was kind of sad for me, but as usual, when I'm wrong, I console myself with remembering that science is about finding truth, not about being right or wrong. So treating it as a teaching moment, we went on, and here's a partial summary of some of our results. So how do you quantify, how do you go beyond the pictures? So the two properties that are shown here are the average change in the height of the flux tube over kind of the inner half a kiloparsec. That's shown by these black curves. And then how much mass has been evacuated from the flux tube. So what happens is that in addition to this drainage effect that I mentioned, the cosmic rays are tremendously overpressured at the site of their injection, and they drive a gas flow out along the tube. We have open boundary conditions, outflow boundary conditions, and so the gas leaves. And so they all, to some extent, display the same feature of a rising flux tube and a declining mass on the tube, which is what allows it to be buoyant. So there are 4 simulations here. So B streaming and B diffusion are both simulations with a strong magnetic field, but streaming transport in the streaming case and diffusive transport in the diff case. And both simulations display a slower rise than the models with either diffusive transport or advective transport. But this seems to be due to a combination of the transport and the energy cost of bending this rather strong field. So there's a strong stabilizing effect of magnetic tension. And you can see that the strong field with diffusive transport does almost nothing as far as elevating the tube or evacuating mass. The diffusive and advective models both have dramatic effects. In 100 mega years, the tubes have actually risen by almost a kiloparsec. They're sort of out the top here. And the masses have gone down by a lot. They've plunged to 1/10 of what they originally were. So we do get a dramatic effect on a shorter time scale.
Can I ask a question?
Yeah, please.
Yeah, is the magnetic field strength different between the C cases and the B cases? If you had a strong field with the advection, would that also be damped out or limited in growth?
A strong field with advection. So if we had a B advection, so the magnetic fields in the advective and diffusive cases, C advection and C diffusion, are the same. All that's the difference between these two, C diffusion and C advective, is that we dialed the diffusivity way, way down by 4 orders of magnitude in the advection model. The streaming, B streaming, has a stronger field than either C diffusion or C advection. And what the B diffusion run shows, which also has a strong field, is that part of the, the sluggishness in these B runs is due to the strong magnetic field. It's not all in the transport. It's also in the magnetic field. Does that answer your question?
Yeah, thanks. Yep.
Great, thanks. So we recovered cosmic ray buoyancy and this puzzling stabilization of the Parker instability by a stiff cosmic ray equation of state is, in my mind at least, resolved. in order to do this, we had to resolve the third dimension. If you do it in 2 dimensions, you're asking this flux tube to, basically lift this enormously heavy atmosphere. And it just works much better if you allow this flux tube to slither through the flux tubes that are not loaded with extra cosmic rays. So it is important to resolve that third dimension. Okay.
And if you allow for the third dimension, isn't that called interchange instability or something else?
Yeah. So the most unstable Parker modes are sometimes called interchanges because, due to the stabilizing effect of magnetic tension, they're long wavelengths. So can you guys see my hands? Probably not.
No, not yet.
So if you want to look at the most unstable modes of the Parker instability, so here's a demonstration you can do at home or wherever you are. So put your pointer finger, your second finger next to your thumb, put one over the other. So those are your flux tubes. Now roll them over each other, but at the same time, rapidly separate them. And that is the characteristic flow associated with the most unstable Parker mode. So you roll 2 flux tubes over each other, and there's and most of the motion is actually in the direction along the magnetic field. So this actually wasn't shown by Parker, it was shown a long time ago by Newcomb. So so you're right. This long wavelength rolling one flux tube over another is the most unstable mode. And Parker was well aware that you need the third dimension, and you can actually show analytically that the most unstable modes are actually in the limit of 0 wavelength in that second horizontal dimension. Okay, so I think we understand this equation of state issue better. We did speed things up. So 100 mega years is still a long time, but it's not as long as 500 mega years. And so you can ask, well, does the Parker instability make a difference at all? And it turns out that it does, because we also did some runs where we launched this cosmic ray injection into a Parker stable background. And what we found then was that the tube would rise, but then it would level off or even sink back to where it was. So if you prepare the ground with the Parker instability and then give it a kick, that's the way to get these really dramatic results. Okay. So I'd also like to show you some effects of partial ionization. And this is a paper that was led by Ryan Farber, a student in Mateusz Ruskowski's group. We all collaborated, and we did a very simple thing. So we turned off streaming. We looked at just diffusion. And we looked at 3 cases. So one with a tiny diffusion coefficient, basically an advection model. Then a model in which the diffusion coefficient was the same everywhere in space and about equal to the Milky Way value. And then a model that we call the decoupling model, where we don't track the ionization explicitly in the simulation, but we assume that where the gas is cold, it's also weakly ionized. So we used temperature as a proxy for weak ionization, and we made the diffusion coefficient 30 times bigger in the cold regions to reflect the fact that the intensity of the waves would be either in the extrinsic turbulence model, the waves would be kind of eroded by ion neutral damping. So we put in a bigger diffusion coefficient. And so I'm going to show you 2 of our results. First, just kind of what the disk looks like. So in the case that the cosmic rays are frozen to the gas, they produce this thick disk. In the case of diffusion, they're able to separate themselves from the gas. And in the case of decoupling, these high density condensations form because cosmic rays don't resist their formation. The cosmic ray pressure gradient is smoothed out by the large diffusivity. And this prints through to both the star formation rate and to the ability of cosmic ray pressure to drive any kind of outflow. So here are the results for the advection, diffusion, and decoupling models of how the star formation rate compares and how the mass flux compares. And now these are at 3 different heights because, sometimes the mass comes back. But let's look first at the star formation rate. So with the advection model, where you have that puffed up disk, you get a much lower star formation rate. It really works well at suppressing star formation, but there's essentially no outflow associated with it. So galactic winds may be a form of star formation feedback, but star formation feedback does not require galactic winds. In the diffusive model, the star formation rate is significantly bigger, 2 to 3 times bigger, and there is a little more of an outflow, although by 5 kiloparsecs, a lot of that mass has fallen back. And in the decoupling model, the cold gas is left behind, so the star formation rate is even bigger, and the actually more mass, slightly more mass leaves in that case, in the decoupling case, because the cosmic rays can effectively diffuse through the densest gas and just drive out the low density gas. But the difference in mass loss rates between these two is very small. The main effect is their effectiveness in suppressing star formation. Okay. So now I see my time is being eroded faster than cosmic rays can erode anything. So I want to tell you briefly about the bottleneck story. So back in 1971, John Skilling, one of the early pioneers in this field, said, well, okay, so cosmic rays are streaming down their pressure gradient along a magnetic flux tube, and the density goes up along that flux tube, which means that the cosmic rays ought to slow down, which actually reverses their pressure gradient. So now they want to stream the other way, and they excite, instead of exciting waves that are streaming down their pressure gradient, they want to excite waves that are streaming in the other direction. And these two things just cannot be reconciled. And so what must happen is that the cosmic ray pressure just goes flat. There are no waves. The cosmic rays just decouple from the thermal gas. But it wasn't until 2014 that Josh Wiener, a student working with Peng Oh, who later worked with me as a postdoc, was actually able to show this in a simulation. And so the basic setup here, both in Josh's work and in Chad's work, which I'll tell you about a little bit later, are so you have some cosmic ray source, which is magnetically connected to a medium that has a cloud in it. So the cosmic rays leave the source and encounter the cloud. So here's this one-dimensional setup where the cosmic rays, so here's the density, here's the Alfvén speed, and here's the evolution of cosmic ray pressure or cosmic ray energy density over 9 million years. And what happens basically is that the cosmic rays build up this pressure plateau. When they reach the density maximum, they re-engage, develop a steep gradient, which actually accomplishes a lot of heating, and then go streaming away at the other side of the cloud. So this does two things. There's a lot of heating associated, which tends to kind of erode the cloud here. And then this pressure pulse actually imparts momentum to the cloud. So Chad looked at this with the ultimate goal of talking about a multi-phase medium, which I'll show you in the next slide. But we did some 1D studies first, and we considered a partially ionized cloud instead of a fully ionized cloud. And the main reason I included these two simulations is to show you what fine scale resolution you need to get the thing to converge. So here's 2 parsec resolution. And so you can see the flat, the cosmic ray pressure going flat, then this drop, flat within the cloud, and now re-engaging on the other side. So the Alfvén speed actually goes up inside this cloud because the plasma density goes down, the gas density goes up, but the plasma density goes down. So the bottleneck actually forms on the other side of the cloud. Now, if you do it at a quarter parsec resolution, and this turned out to be the resolved scale, you get kind of similar pressure elevation on the side close to the source, but you get a very different pressure drop. You get a much bigger pressure drop, which means you get a much bigger momentum impulse imparted to the cloud. And you really need this quarter parsec resolution to get it right. Here's a little more on the momentum deposition. It turns out that there's, so these are all fully ionized clouds, two-dimensional. And it turns out that there's kind of a sweet spot for maximum acceleration. So these are, each color here represents a different magnetic field strength. And what happens when the magnetic field is really weak is that the field lines just kind of get dragged around the cloud. The cosmic rays encounter the cloud and they flow around it. And they drag the field lines with them, and you don't get very much of a pressure buildup. If the magnetic field is very strong, it resembles the one-dimensional case. The cosmic ray front arrives before any kind of gas pressure pulse can do so. And so that turns out to reduce the amount of momentum that can be imparted to the cloud. So there's kind of a sweet spot around 5 microgauss for these parameters, where the momentum impulse and the final velocity are increased. And the story is basically the same for the heating, because the heating depends on the pressure gradient. And then here's what happens if you, instead of considering one cloud, if you consider a clumpy medium. So the source is down here. You can see the field lines with these arrows. These contours here represent clumps. The light contours are overdensity by a factor of 10. There's some overdensities by 100 lurking in here, but I don't really see them. And you can see that this very irregular front develops very strong gradients as the cosmic rays force their way into a medium with varying alphane speed. Now, I think this situation is pretty generic, whether due to tangling of the field or just clumpy multi-phase gas. I think it may be more the exception than the rule that the cosmic ray pressure gradient and the plasma density gradient are co-aligned and going in the same direction. And what this implies, if you take this bottleneck picture seriously, what this implies is that cosmic ray coupling to the medium is really very intermittent. You have these large regions where the cosmic ray pressure is just flat, there are no waves, there's no heating, there's no force. It's also, in addition to being spatially intermittent, it's probably temporally intermittent because it takes about 1 alphane travel time to set this thing up. So that's one message from our work on bottlenecks. The other message is that you really need to resolve these fronts where the gas properties change abruptly, not just to see what's going on in fronts, although that's interesting in itself and generates a lot of observational predictions, but also to just get the overall pressurization and momentum input right. You really have to do that. So, I was going to talk about an Eddington limit for cosmic rays. Do I have time to do that?
Yeah,
Maybe
5
yes. Okay, so this work's pretty recent. So there was this very provocative paper back in 2008 by Aristotle Socrates, Enrico Ramirez Ruiz, and Shane Davis. And they said, well, suppose you had a starburst galaxy that was just pumping out an enormous flux of cosmic rays. Could you blow the whole interstellar medium away? And would that kind of set an upper limit on how bright a starburst galaxy could actually be? So I was always interested in this paper, but I had some quibbles with how they did the propagation. So we looked at it again, and we set it up in kind of a different way, by analogy with Parker's argument for the solar wind. So Parker argued that there had to be a solar wind because he made this very simple model of an isothermal corona in hydrostatic equilibrium, and he showed that the pressure reached an asymptotic value that was much higher than the interstellar value. 6 orders of magnitude or something. He said, well, okay, this cannot remain in equilibrium, it must be expanding. And that was his initial argument for the solar wind. So we set up an analogous problem. We said, well, suppose you had a round galaxy and there was a central molecular zone with a high star formation rate that set some sort of base pressure at the edge of that central molecular zone. And suppose that the flux of cosmic rays out of this thing was so high that you had a cosmic ray supported atmosphere. Could that configuration always be confined by a circumgalactic medium? And we looked at this for a variety of transport models, guided by parameters to the extent we knew them for 5 different galaxies. And this is kind of what the models look like. You can do most of them analytically. So here is base cosmic ray energy density. And here's the confinement radius. So we chose a circumgalactic pressure. These are the 5 galaxies, M82, a starburst, the Milky Way, a Milky Way-like galaxy, the Large Magellanic Cloud, a dwarf starburst, and then one of those humongous ultraluminous infrared galaxies seen at high redshift called DRC-8. So each color represents a particular galaxy, and you can see what happens as you approach. So these vertical lines here represent the theoretical maximum confinement pressures or Eddington pressures. You can see that the confinement radii really go up as you approach those limits, and the confined mass goes up, and the ratio of base luminosity to final luminosity. So remember, the cosmic rays are losing all their energy to heating, or losing a fair fraction of their energy to heating. This kind of shows. So here in this case, 95% of the initial luminosity is expended in creating this Eddington-like halo. If you add up all the results, you basically find that the only galaxies that are anywhere near their Eddington limit are the dwarf starbursts, NGC 4449, and to some extent, the Large Magellanic Cloud. Milky Way-like galaxies, M82, DRC-8, they're all far below their Eddington limits. So I think the Eddington limit it's a well-founded concept, but it doesn't seem to apply to most of the galaxies that we see. And really the only way to get anywhere close is with streaming transport, because that's actually the transport model that where the cosmic rays suffer the least losses and sustain their pressure to the largest distances. Okay, so here's a summary. So cosmic rays carry a major fraction of interstellar energy density. That's well established. They're confined magnetically and coupled collisionlessly to the thermal background by a magnetic field. I think that's also well established. And I think I don't know a good alternative for scattering other than these kinetic scale waves, whether they're excited by the cosmic rays themselves or extrinsically generated in a turbulent cascade. And I hope I've convinced you through these examples, and we have more, that the effects of cosmic rays are really very sensitive to these basic assumptions we make about their transport. So we really have to get that right. And here's some examples of where this really shows up. So what are the next steps? So here's some challenges now and in the future. So we're beginning to go beyond the fluid model by treating different parts of the energy spectrum, cosmic ray energy spectrum. And this is especially important if we want to refine observational predictions. So I'm thinking both of gamma rays, and I'm thinking of the lower energy cosmic rays that drive chemistry. I think this is a way underexploited set of probes of what cosmic rays are doing. There's a lot we could do to improve our understanding of these scattering fluctuations. And I'm thinking especially of the nonlinear effects and how they interact with the background turbulence. And this will be very important for choosing the right propagation models, seeing how propagation changes as you go to different parts of the interstellar medium. I didn't talk about this at all, but there are some special effects near sources where cosmic ray fluxes are high relative to magnetic energy densities. And then finally, there's this multi-scale challenge. So even once we have a fluid theory, we need adequate spatial resolution to resolve interfaces, treat the effects of many clouds. We need subgrid prescriptions, and we need adequate spatial resolution. But I think given all the great data now and imminent, and our increasing ability to simulate and think when we have time, I don't think there's ever been a better time to do this. So thank you.
Okay, great. Thanks for a very nice overview of a complicated subject that always, I guess, people off. And I guess we can have questions now. Lots of questions, and we have one hand up from Susume. So Susume, why don't you go and ask your question?
Yeah, thank you for the very nice overview. If transport by streaming is important, as you said, there will be this associated heating due to alpha N wave generation and their subsequent damping. Would there be a good observational way to prove that this heating, alpha N heating, is occurring instead of due to particle collisions like Coulomb collisions?
Yeah, so the heating tends to be important in fronts. So I can point you to a couple of things which I didn't include in my talk. So in 2013, Josh Wiener and I considered heating the warm ionized medium. So this, thick extraplanar diffuse ionized gas in the galaxy by this collisionless cosmic ray heating. And we were motivated to do that because Ron Reynolds and other observers had argued that there seemed to be a heating mechanism which goes up with decreasing density, which most of them do not. And we actually got a good fit, both a good quantitative fit with, I think pretty secure assumptions and observational input to the inferred heating rate of the warm ionized medium. On the theoretical side, in Josh's first bottleneck paper, so this was 1D, we predicted line strengths in the far side of the cloud where the cosmic rays have re-engaged, and you get this big cosmic ray pressure gradient. And there were a number of models of line strength ratios. For example, collisional ionization equilibrium doesn't work at all. And we actually did as well as the best models. So that, that doesn't uniquely prove that it is cosmic ray heating, but it also doesn't rule it out. But I would really like to develop more. I would really, now that we have Chad's work and a better feeling for what these interfaces look like, I would really like to go back. There's also a prediction in John Everett's paper, which is a 1D model taking 1D steady state model that takes variable ionization into account. Yeah, so that's what I'm aware of, but I think it's extremely important to come up with diagnostics and test this model.
Yeah, thank you very much.
Thanks for the question.
Okay, thanks. Oh, Brian raised his hand. Okay, Brian, go ahead.
Hi, Ellen. Thanks again for the nice talk. Could I know you probably deliberately glossed over it, but it would be maybe important to know the details, or some of the details, if you could really summarize it quickly, that go into these cosmic ray plus MHD numerical models, because there's a lot of assumptions to go into those, right? In terms of, the streaming is really projected along the local magnetic field. I think the diffusion as well, do you assume it's isotropic, or is the diffusion so projected along the magnetic field? And
yeah, so I'm not sure whether you're asking more about the derivation of the fluid equations from the the Fokker-Planck equation, or how you put
the physical assumption. The physical assumption.
Yeah, So the main physical assumption that goes into deriving the fluid theory is that there's frequent scattering. So there's a hierarchy of timescales where the shortest timescale is the scattering time. Then there's an intermediate timescale, which is basically the density or the density or pressure length scale divided by the speed of light, the speed of an individual cosmic ray particle. And then the longest time scale is for the overall evolution of the system. So that's what's assumed in coming up with these expressions. Okay. And then as far as streaming versus diffusion, you can derive transport equations and fluid equations from either. And I think maybe some good guidance for this, but it's only partial. Goes back to the 1975 paper of John Skilling, where he considered. So let me back up for a minute. So the streaming instability, as you know, only excites waves that are traveling in the direction down the cosmic ray pressure gradient. But you might expect interstellar turbulence to be balanced, have equal intensities going in both directions. And it turns out that cosmic rays feed energy to the waves that are traveling down their pressure gradient, and they absorb energy from waves that are going up their pressure gradient. So Skilling derived a sort of weighted wave frame velocity, which so it's weighted by the intensities of waves traveling in both directions, and you can go to the balanced extrinsic turbulence at one extreme and the streaming model at the other extreme and derive fluid equations from that. But they're incomplete because they don't really take the energy exchange, or they don't really allow the particles to feed energy to the waves. They do it in instability. So guided in part by work by Reinhard Schlickheiser, I did that in my 2017 paper. Now, to implement this numerically, so as far as I know, at least all the treatments that I've ever been involved with have anisotropic diffusion. The diffusion is only along the field line. Some groups kind of put in an extra diffusivity that represents field line wandering, but it's not really tied to a particular model of the magnetic field, more kind of a subgrid model. And then there are these two basic ways. So the main numerical difficulty with implementing streaming is that when the cosmic ray pressure gradient changes direction, how you accommodate, suddenly having all the dynamics going the other way. And the first workaround for that was some work by Pratik Sharma back in 2010, where he, instead of having an abrupt transition, he introduced this kind of smoothing length. And so there was a transition described by hyperbolic tangent. But more recently, Peng O and Yanfei Zhang, and then separately, a group led by Christoph Frommer, have developed a method that's based on the two-moment method in radiative transfer, where you evolve both the cosmic ray energy density and the cosmic ray flux with a reduced speed of light. And that's actually what that's implemented in Athena, and that's what Rourke used for his simulations. Does that help at all?
Yeah, no, I mean, I understand that.
I know you understand everything, but
maybe I can be a bit more controversial and say,
yeah.
and say how much, or do you think that is? Do you have any concern over the very much one-dimensional view of all of those approaches? If you see what I mean, that you're locally projecting onto the local magnetic field line, which of course is already a crude approximation in itself.
Well, yeah, so it really depends, I think, on how stochastic the field lines are. I mean, I think that if the field is only changing slowly on the scale of a cosmic ray gyroradius, that the cosmic rays basically do follow the field lines. Even things like a curvature drift or gradient drift, they're of order the gyro radius over the length scale. They're important certainly in shock fronts. We know they're important in the solar system, but it's very hard to get evidence that they're important in the interstellar medium. We just don't observe the field on those scales. But if the field really is stochastic and really does vary over a fiducial gyro radius, I don't think you can really talk about the cosmic rays being tied to a field line, and it becomes much more isotropic. And, the sort of zero order thing to do would be to just say, okay, they're relativistic fluid, gamma equals 4/3. Assume they're scattered by something. But, I would actually love to do the plasma physics. I'd even love to do the plasma physics correctly for the so-called turbulent damping. So, yeah, I think there is a bandage to look under there. Does that make sense?
Yeah, no, I agree. Thanks, Ellen.
Okay, thanks. Any other questions? If not, maybe I can ask a couple of my own questions, but anybody else wants to ask a question? Okay, so Ellen, do you think there are any particular observations that would be relevant? I guess one of your students talked about gamma ray observations of other galaxies for setting limits on how many cosmic rays there are and maybe how they're spatially distributed. And you can look at synchrotron radio halos to see what the electrons are doing. Are there any observations you think are important for constraining the plasma physics or on large scales?
Well, I think the results that we're all trying to deal with are, so Phil Hopkins' group at Caltech, the fire simulations, this began with a paper in 2019 led by TK Chan, where they had models of cosmic ray feedback. So they put it into galaxy formation and evolution models, and then they calculated the gamma ray emissivity resulting from those models, and they found it was much bigger than the gamma ray luminosity measured by Fermi. And okay, so how do you reconcile this? So they showed that you can actually get a better fit to the Fermi models if you increase the diffusion coefficient by a large factor. I think about a factor of 30. Now, of course, what this does is it reduces the efficacy of cosmic ray feedback because the cosmic rays just aren't as well coupled to the gas. When I saw the result, I wondered if it might really be saying something about the magnetic topology, that maybe the cosmic rays aren't, maybe the cosmic rays are sort of avoiding the clouds because they're following magnetic fields that are avoiding the clouds. Then I gave a Zoom talk to an audience at the University of Aachen, and they told me about their work trying to fit trying to make the ionization rate come out in diffuse clouds using the cosmic ray fluxes that are measured, by Voyager outside the heliopause. And there, they don't get enough ionization. So, that goes in the opposite direction. That says you have to get more cosmic rays into the clouds. So, so this issue has really not been sorted out. I think that the large diffusion coefficients that seem to be necessary to make the fire simulations work, they're really not compatible with galactic cosmic ray propagation data. I think we do have a pretty good estimate of the diffusivity based on observations and cosmic ray codes like Galprop. I don't know if there's someone here who wants to go into any warts on that. I don't know, but I'm pretty convinced that we know what the diffusivity is. So I think, that's a big challenge. And, all diagnostics that depend on magnetic fields, there's sort of a double uncertainty there, what the magnetic field is doing. Do you assume equipartition or what? So as I mentioned, one of the big questions in my mind is whether the low energy, so most of the ionizing and heating, collisional ionization and heating in the interstellar medium that's done by cosmic rays is done by particles of, a few to tens or maybe 100 MeV, so subrelativistic particles. And I don't really know, maybe someone here has an opinion of whether they should be considered part of the same population. So if you have a galaxy like M82, where the cosmic ray energy density seems to be about 600 times bigger than it is in the Milky Way, is the low energy cosmic ray density also 600 times bigger than ours? And I think that a way to get at this maybe is cosmic ray driven interstellar chemistry. And there's certainly been a lot of really fine work on that, but I think there could be more. Does that help?
Yep. That's any thoughts from the audience or nope. So it looks like any other questions? If not, maybe I could be extra controversial for a second. Rashmi, is it okay if I share screen?
Yeah, absolutely.
Okay, so what happened was I was at the High Energy Astrophysics Division meeting, and Phil Hopkins gave a very nice mid-career prize talk, and one of his topics was cosmic rays, exactly what Ellen was talking about. And I wanted to know if Ellen had any opinions on some of his statements, because there's the controversy out there. So I'm going to try sharing a screen, and then let me see if I can do it right. So let's see, this is his conclusion about cosmic rays. He was saying that they don't seem to be that important, the ISM, in terms of pressure and dynamics and things. Well, for pressure, yes, but setting the conditions for star formation and galaxy evolution, but they could be a big game changer if the scattering coefficient is correct in the outer halo on size scales of 10 to 200 kiloparsecs. And I was wondering, what do you think about that statement, Ellen? Is that
so yeah, so something actually this slide flashed up by accident. I was going to show it if I had time.
Okay.
So,
do you want me to stop?
No, it doesn't. No, I can just say what it is. Doesn't matter. So what happens to cosmic rays when they leave the galaxy? So whether they drive a wind or are carried out in a wind, they arrive at the termination shock, just exhausted, with their energies greatly reduced by adiabatic expansion or possibly heating in the case of streaming. And so Chad and I did a study of cosmic ray acceleration at the termination shock. And part of the motivation was to revisit this claim that the ultra high energy cosmic rays could be accelerated there. And we don't think there's enough time for that. But if you make sort of standard assumptions about the efficiency of shock acceleration, something like 10% of the luminosity in the wind could be converted to cosmic rays, and they just go pouring out. Most of them don't diffuse back to the galaxy because they're being pushed upstream by the wind. And they just go pouring out into the CGM, and they can affect the pressure and the temperature there. Now, I'm not sure why Phil thinks that they're a game changer in the halo, not so much in the ISM, but he's entitled to his opinions. And yeah, so I'm not, I guess I don't understand the basis for the second statement, but it does look very controversial. So maybe you could amplify a little bit what it meant there.
Yeah, and I was really curious about the exactly second statement, unknown physics, and what he was saying was, and maybe other people can chime in on this. He was saying if we have like sort of extrinsic turbulence, he says there's no way, like with a typical MHD cascade that we talk about, that you can get the right diffusion coefficients and the energy dependence of the diffusion coefficient, in particular this, I guess. Is that a surprise to you or people like us?
So I think what that refers to is that I mean, in a typical turbulent cascade, the energy resides at the larger scales.
Yeah.
So if you apply that to the scattering problem, you would infer that if you assume that every cosmic ray, that the turbulence that it mostly sees is the turbulence the size of its gyro radius, that would imply that the higher energy cosmic rays are more scattered. And they should actually be confined to the Milky Way for longer than the lower energy ones.
Yep.
So, so something else must happen. Now, with the interstellar turbulent cascade, so actually, I think Alex Lazarian and Huirong Yang and Ben Chandran kind of came to this realization independently in the early 2000s. So the MHD cascade in a strong background magnetic field is very anisotropic. And where in that the perpendicular length scales, perpendicular to the magnetic field, are much shorter than the parallel length scales. What counts for the resonance, for gyro resonance, is the parallel scale. So if you ask how cosmic rays are scattered by the MHD Alfvén wave cascade, the answer is very poorly, because by the time you get down to the scales that they resonate with, the perpendicular wave numbers are so short that it's like the picture I showed with the tiny little coils. They really hardly see that stuff. So Chandran had the idea that clouds kind of act as magnetic mirrors, and they're the main agents of scattering. And Yan and Lazarian argued that if you take compressibility into account, the Alfvén wave cascade generates another cascade of compressive MHD waves that is much more isotropic than the Alfvén wave cascade. Now, this idea has been called into question by some recent numerical simulations by different groups, actually. Hui Li at Los Alamos and Van Guo did some of that work. And Elliot Quadrant and Philip Kempsky also did some of the work. Actually, Philip Kempsky was just here. He's probably flying out at this very moment. But he was visiting here for the last couple of days. So yeah, so it's actually very difficult to separate the Alfvén waves from the compressive waves in a numerical simulation, and it's not clear that the cascade really is generated in the way that was assumed. So I think, you know, the final word on that has not been written for the extrinsic turbulence model. But anyway, that cascade has different properties from the Alfvén wave cascade, and you know, it may be maybe a little more promising.
Okay.
So is that a reply to Phil? Does that understand?
Yeah, I think so. Yeah, I'm out of date on this, so that's, and he had one other point, if you want. He thought that self-confinement didn't work that well either. Does this make sense? He says the amplitude of the waves is not either high enough, I guess, and the spectral shape is wrong. And
yeah, so that's why okay, so self-confinement has really never been claimed to work for energies higher than 1 to 200 GeV, and that's because the rate at which the waves are excited depends on the number of cosmic rays that can resonate with them. And as you go to longer and longer wavelength waves, you require cosmic rays with larger and larger gyro radii, and there are fewer and fewer of them because of the nature of the energy spectrum. So it was recognized, I think, originally in 1971 that by Kulsford and Cesarsky, that some other mechanism for confinement would have to kick in. And actually Pasquale Blase has done some work trying to explain, possibly identify a spectral feature that would correspond to that crossover. And then so at the lower energies, and so I think, you know, self-confinement for the energies that matter, you know, sort of for determining the cosmic ray pressure, that is still in a domain where self-confinement should work. So that's really what I was alluding to in my slides about understanding the damping, the nonlinear effects a little bit. We don't really know what saturates the instability. We assume that the instability kind of saturates where growth balances damping, and that the cosmic rays kind of relax to the extent that they make the waves marginally stable. But it would be really great to have a more fundamental understanding of that. However, I'd like to reach that understanding before giving up on it,
Yep.
if that makes sense.
Yeah. Okay. And all right. And just for fun, I guess he said these were some of his ideas, I guess, scattering off strong structures. Is that like Ben Chandran? I mean,
so
like-
I think, yeah, I mean, I think Ben associated those structures with density perturbations, clouds. But there's an idea which I first saw in connection with ultra high energy cosmic ray propagation, which is that, so the ultra high energy cosmic rays are propagating through the intergalactic medium, and that they scatter strongly off structure. So Komiko Kotera, I think, worked on that for her PhD thesis under Martin Lemoyne. And maybe this also applies at, this could be another manifestation of nonlinearity, that, you generate a continuous spectrum of uncorrelated waves, but then they interact, give you some sort of more intermittent structure. So yeah, I wouldn't rule that out at all. I think it's an interesting possibility.
Okay,
So,
cool.
yeah.
All right. I think that's pretty much all he's saying. Thanks. And one last question, just again for myself, to what extent, whoops, wrong. I'm going to stop sharing if I can figure out how to do that. To what extent, like when people do MHD simulations of galaxies, you have these chimneys that open up from super bubbles, and presumably the field is organized, and that's different from standard turbulent field. Does that enhance cosmic ray transport out? Is that taken care of appropriately, or that's not so relevant? So having bubbles and winds.
No, I think it is. And so actually, so Rourke Habiger, the student who did that cosmic ray injection model, so he's collaborating now with Ryan Farber, who wants to put, the effects of multiple injections into a more global simulation. And, this is exactly what they want to see. They want to see the field going vertical and opening up. And so what happens in the models of self-generated winds, where you start with a field in the plane, is that you inflate the field, you sort of drive it out, and then it goes to a more vertical configuration. Does that answer your question?
Yep. Yeah. Thanks. So I've talked way too much. So
No, thanks for all your questions. Thanks everybody for all their questions.
Yeah, I do think there are lots of communities all converging on the same thing, so we should all be talking. It's important. Does anybody have, or Andrei Bykov or anybody, cosmic ray experts, have any thoughts here?
No, thanks. It was very, very interesting indeed.
Thank you.
Okay. Thanks. So,
yeah, thank you, Alan. That was a really excellent talk. And
thank you. Thank you for the opportunity.
Slides so that we can post them.
Sure. Can I just email them to you if it's not too big of a file? Okay.
No, not a problem. Yeah.
Okay. Yeah. I will attempt to do that. Yeah.
Although we should probably close the session. People are leaving.
Yeah, I think so. Okay. Who's going to talk next? Can you?
Yeah, I just want to remind people that next week not next week, but April 19th, Hidetoshi Sano on ALMA CO observations of shocked filaments and young supernova remnant shells. So hope to see people there. Just please join. I'm just going to put it here in the chat. Sorry.
Okay. Thanks, everybody.
Yeah.
Thank you again, Ellen.
Thank you. Thanks. Thank you, everyone.
Yes,
okay. Bye-bye.